What did we come up with? How many states was your final solution to this problem?
We got three.
Three?
We also had three.
Yeah, that is the right answer. Looks something like this.
Yeah, exactly.
Nice. All right, so last time we introduced this idea that we could potentially reduce a DFA into a smaller DFA. So now we're actually going to start formalizing this process. And this is going to be the most difficult algorithmic process we've seen yet so far in this class. So hang with me. Hopefully this makes sense by the end of it. If not, we'll have some examples. We can stay here as long as we need to for this to make sense. So we need to define a couple of terms first. We need to talk about distinguishability. So we're going to define what it means to be indistinguishable and then what it means to be distinguishable. All right, two states are indistinguishable if and only if. From both of those states, you could think of every possible string in the language, either leading to a final state or a non-final state. It doesn't have to be the same state, but for every string in the language, if you reach finality from two states and non-finality from two states on that same given string, then they are indistinguishable. You might as well be in one or the other, if that makes sense, because the finality of where you end up does not change. So that's the concept of indistinguishability. So that's kind of the intuitive definition. So here is more of a mathematical definition. The transition, and it's the star closure of a transition, so 0 or more transitions from P consuming W is a subset of final, implies that, so P and Q are the two states. So state P is indistinguishable from state Q if for all possible W, if that W, that part of that string, leads you to a final state from one state, then the same string leads you to a final state from the other. Same idea, if it's not final in one, then it must be non-final in the other. So this is more like what you would see in the textbook. You see that color, it was snipped directly from the textbook, which is how they would introduce this. So if that's indistinguishable, then we can also define distinguishability to be there exists some string, we'll call that string W, such that from those states, you have a differing finality. So again, we have state P, we have state Q. If we apply W to P and Q, one of them ends up final and one of them ends up non-final. So for some state P and some state Q, you apply W from there in that DFA. One of them leads to a final state, one of them leads to a non-final state. We can kind of use a truth table formality to say that, all right, we have a pair of states. They're either distinguishable or indistinguishable. There's no neither distinguishable nor indistinguishable or both distinguishable and indistinguishable. So it's either one or the other. So the entire purpose of this algorithm is to find and combine all pairs of states that are indistinguishable. Questions on kind of the preliminaries, the goal of the algorithm before we dive into how exactly we are going to try to measure this and find those distinguishable pairs? Good so far? All right, we're going to go through exactly how to do this. So finding indistinguishability or finding distinguishability, which one do you think is easier?
Indistinguishability, I feel like.
What makes you say that?
Like it'd be easier to find if two places lead to like the similar thing rather than if they're leading to different things.
Okay. Valid. Other thoughts? Agreement, disagreement? Actually completely wrong. It's much easier to find distinguishable pairs. And the reason for this is that in order to show this, we have to show it for all W. How many W are there going to be?
Possibly infinite.
Infinite. There are going to be ways to go throughout that DFA for any possible string of any possible length. We know that every string would be in the star closure of that language, so we have to basically be able to map it to every string to be able to say, well, these are indistinguishable. That is a nasty proof because you can't just exhaustively go through them all. On the other hand, distinguishability is proof by example. All you have to do is find one such W such that state P, when applied to that W, leads to a final state, and state Q, when applied to that W, leads to a non-final state. So you just need a single example, and you have shown that that pair of states is distinguishable. And we know now that if a state is distinguishable, then it can't be indistinguishable. So if we could find examples for all of the ones where examples could be found, what's left over is indistinguishable. So we're going to take that route to try to construct this algorithm and find indistinguishability. So indistinguishability will be found by finding distinguishability. So the first part of this is to find and remove any inaccessible states. And this is why when I introduced you to the first example, there was such a state that we could not reach. It seemed ridiculous when you looked at it, but these are states that we just don't even want to consider. So how would we do this? Let's say we have a digital representation of a DFA. How could we actually go through and find if all of the states are usable or not, or accessible or not? Any thoughts on designing that algorithm? What does it mean to trace a path? I love that idea. It sounds kind of like you're drawing it on paper. What would that mean digitally?
Trying to find a string that won't reach that, or trying to see if a string that doesn't. We're trying to. If there's a state that cannot be reached by any string.
You'd have to enumerate all possible strings to be able to determine that. It's a good idea, but your algorithm will never terminate.
Do the states know what's pointing at it?
You can absolutely navigate those edges. So something like starting at the start state, enumerate all edges out of that start state. That will show you everywhere that is reachable in one step from that. So we're going to label our states as either visited or not visited. The idea is we're going to visit the first state and say, all right, where can we reach in one step from there? Add those to a queue of nodes to visit. So let's say we have some DFA with some inaccessible state. I want to go back, maybe I want to go back. We'll just say we have this on an A, we go to Q1, on a B, we go to Q2. We go here on an A, we go here on a B, and there's some useless Q3 out here that goes here on an A and here on a B. So we have our inaccessible state Q3 here. So we would keep track of a Q. The very first part of it would say, let's put Q0 into the queue as the initial state. We're going to visit that state. All right, where is everywhere that we can get from Q0? On an A, we can reach Q1. On a B, we can reach Q2. So we're going to add Q0 to the list of visited states. And then we have an unvisited here. That would be Q1, Q2, and Q3. All right, so as we do this, we're going to remove the Q0 from the queue, adding it to visited, saying where is everywhere we can get from here, Q1 and Q2. We are going to remove Q1 and Q2 from unvisited and put them in the queue of states to visit. All right, now we're going to visit Q1, which says we dequeue it. We're going to put it into the visited. Where is everywhere that we can reach from Q1? I guess we need something to do on a B. And here we need something to do on an A. Sure. Truly be a DFA. So everywhere we can reach from Q1 is that we can get to Q1 or Q2. We check if either of those are unvisited. Since they are not, we add nothing to the queue. We don't want to repeat work that we've already done. We could add Q0, but Q0 isn't going to go anywhere it didn't go the first time we visited it. So we're done. Everywhere that we can get to in a single step from Q1 is either visited or in the queue. It's not in the unvisited list. So now we dequeue the Q2 and visit that. Whereas everywhere we can get from Q2, well, we can get to Q1 or Q2, which are either in the visited list or in the queue. Now we see that the queue is empty, which tells us that everything left in this unvisited list is unreachable. And this means that we're dequeuing and visiting each state at least once. So as long as this, I'm sorry, most once. So this process will terminate as long as there are a finite number of states. And it'll be pretty efficient. So this is kind of outside of the scope of this algorithm, but rather than just kind of show it to you and put it up there when it says find and remove any inaccessible states. Now I've kind of algorithmatized this so that there is a code process for you to imagine that this is stored. How would this be stored if you wanted to store this in some kind of data structure? What data structure would you use to store this graph? Do get answers.
Like a bag,
What, sorry?
a bag graph.
Yeah. So you could instantiate a graph, but how does a graph store it underneath the hood? So usually there is a graph structure built into a language, but if you had to do it from scratch.
Like nodes, kind of like a linked list with a tree.
Yeah, either, so we call them an adjacency list or an adjacency matrix.
Yeah.
The adjacency matrix is just a two-dimensional array where each row represents a from and each column represents a to, and you would have, this would be binary, either true or false if there exists, or maybe you have a character that says the character that is consumed. You can reach from Q0 to Q1 on an A. So you would store that as an adjacency matrix. You could use it as a list if you wanted to save a little bit of space, but you were okay with occasionally a little bit more time. You would store only the lists. These now become the froms, and each from has an associated linked list of all places that you can reach from Q0, Q1, Q2, and Q3. So here you would say something like you have a structure that says you can reach Q1 on an A. And that would be linked to the next thing that you could also get from Q0. So you could get to Q2 on a B would be the next element of that adjacency list. So either one of those would be a structural programmatic representation of kind of this visual diagram. All right, so we have the structure to store it. We have the queue for processing. We would just have a list of visited and unvisited. Those can be linked lists. They can be whatever you want for each of these. So that would be how you would implement the concept of finding and removing any inaccessible states. So we take what's in that unvisited list and we remove those nodes and all adjacencies to those, all out edges and in edges to that node. All right. Then we're going to start considering pairs of states. So we're going to loop through and take all pairs of states. If that state is final and the other state is non-final, we know that the pair is distinguishable. We're going to split up the states into what we're going to call equivalence classes, where everything in one equivalence class, as we do this, may be distinguishable still, but we haven't shown it yet. And we are going to loop the following until we go through one of these looping processes and we make no changes in any pairs that are distinguishable, basically. So what did that process look like? For all pairs of states and all characters in the language. So there's quite a few of this here. We're going to be looking at every possible pair across every possible character. So to give you an idea of how much work this is, let's say we have 5 states and 3 characters in the language. How much work is this at most? First of all, how many pairs of states are there?
It's not very factorial, is it?
It is not 5 factorial.
It's close.
It's just-
2 to the 5th.
That would be, so we only care about if we have like a pair that is 1, 2, 2, 1 is that same pair.
Right.
So order does not matter here. If we wanted to list them, let's say we have state 1, 2, 3, 4, and 5. We wanted to start listing them. Could we come up with an algorithm? How algorithmically would you do this? Pair 1 with everything unpaired so far. So we would do 1 with 2, 1 with 3, 1 with 4, 1 with 5. We would then loop around and consider 2, pairing 2 with everything that hasn't been paired so far. 2 to 3 to 4 to 5. We could then do 3 to 4 and 3 to 5 and 4 to 5. What's the pattern?
You have 2 and -1.
Here we have n. How many pairs were there consisting of 1? Four. So we have n minus 1. We don't do something for each of those. We consider them separately. So we're going to add how many pairs with 2 that weren't already counted? That's n minus 2. So we come up with some kind of formulation as such. Do we know how to easily calculate 1 + 2 + 3 up to some arbitrary endpoint? Like, let's say I wanted you to calculate 1 + 2 + up to 100. How could we easily do that very quickly? It should be that keeps coming up so many times in computer science that it's worth it. So here we just set this as the value of n. We say n times n + 1 over 2. That will be a formulation of this, which is significantly easier. 100 times 101 over 2. A lot easier. This is just 5,050. Way easier than going through something 100 times. Or consider this could get significantly worse. So here n is 5. We're going to go up to n - 1. So this n in this case is 4. So 4 times 5 over 2, there are 10. And if we wanted to count, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Same thing. Less work. So that's how many pairs of states there are. But now we need to multiply that by every possible character in the language, because that's how many out edges there could be from that state. Well, there are in that state. So in state 1, if there are 3 characters in the language, let's say they're A, B, and C, we would have an out edge from 1 to somewhere on an A, an out edge from 1 to somewhere on a B, an out edge from somewhere on a C. So when it says all pairs of states and all characters in the language, we're going to cross this, or you can think of it as a loop inside of a loop, to say for each one of these, we now need to consider what happens on an A, on a B, on a C. So pairs of states, we're going to see what happens from a 1 on an A and a 2 on an A. Did those lead to the same finality? Yes or no? For pairs 1 and 3 on an A, 1 and 4 on an A. Remember all that. 1 and 2 on a B, 1 and 3 on a B. Remember that. 1 and 2 on a C. And we're trying to find an example of some character that leads to different finality. Because if we can show that example, then we know those two states are distinguishable. Questions on any of that? Any of that logic of what we're going to be doing? Kind of how to visualize it? Comes up over and over and over and over. I find myself explaining it in just about every class I teach, which is funny. So we're going to compute the transition from P and Q using the current character. So instead of being in one state, you can kind of think of yourselves in 2 states at the same time. Then you make that transition on that character and you find out where do you go. And then you're going to look at where we went. What's the finality of the destination for both of those? If that new pair of states, after we transition from P and Q on the current character, are distinguishable. So you start with just finality, but eventually we're going to look at actually distinguishing the distinguishing classes, these equivalence classes. So start with just finality, but eventually we need to start considering whether they're in different equivalence classes. Then this pair is distinguishable. We found the string W such that if we take that transition, we end up in places of states that aren't distinguishable, right, that are distinguishable. So these states are also distinguishable. So we want these states to be in separate equivalence classes, because we know they aren't the same. Question.
With that formula you just had, I'm sorry, it says like you erased it. Can you show me one more time? Because it's not working for any of the characters that I'm pointing to.
Give me your example. Let's see what's happening.
A, B, C, D, E.
All right, we have
You only want
A,
pairs of 2.
C, D, and E.
Yes, and you only want pairs of 2. N would be 5, right?
For pairs, N is 4.
N is 4.
And the reason is how many pairs with A are there? A can be paired with 4 things,
So you only go
B,
by
C,
that.
D, and E.
Okay, got it. That's what I was getting on.
Yeah, because you start with N minus 1 in this, the number of states minus 1 in this case. So when I said 1 plus 2 plus up to N, that N, I used the same variable, was the N minus 1 from this.
Okay.
Excellent clarification. Yes, I appreciate, I really appreciate that you're doing that, because getting the practice with it and showing that helps you to reach the same point that we're all at as quickly as possible. So that's excellent. So this should be 10 possible pairs again.
We just do N times N minus 1, if you make N 5.
Yeah.
Okay. Cool, because that's the formula that I was using, and I think it's slightly different, I'm trying to figure out what the difference, but.
Yep. Because you basically do a substitution. If this is N times N minus 1, let's make a substitution that says M equals N minus 1. So you make that associated substitution. So this is M and this is M plus 1. So here's how you get something plus 1, when that something is the first thing's minus 1. Great point. All right. So we'll do this once, and then we're gonna loop around and do it again, and loop around and do it again until we do not place any 2 states in separate equivalence classes. If we go through this logic and do no real work, we make no changes to the distinguishability, then we terminate, we are done. We have found the equivalence classes. So if you do this, we know that pairs of states are either distinguishable or indistinguishable. If this terminates having found all distinguishable pairs, then all remaining pairs must be indistinguishable. And that finds all of the states that can be combined in a DFA. How are we doing? Just from this description, I know this is very logical and we need some examples, but just how I like to get a sense of how do people feel about the logic associated with this, maybe set of thumbs, understand it perfectly, could implement it. I think I understand it. An example would show me or not show me if I understand it as well as I think I do. I get the basic idea, but I really need some iteration to understand it better. I have no idea what's going on. Please help. Okay. So let's actually go through an example because examples are good. So we want to reduce this DFA and see if the minimal DFA is smaller than this. Maybe this is a DFA that somebody creates to solve a problem. First of all, just take an intuitive look at it. Does it look like it's a minimum DFA? It doesn't quite have as simple ways to remove states as the last one. So either it's minimum or you need to use a little bit more work to figure out if it is minimum or not. But does anyone see anything as they look at it?
Entire middle section. Like Q1, 2, and 3. You just make the single line go to Q4 with 0 and 1, because I don't see a pattern. That. Like,
How would we get this kind of even number of zeros? versus odd number of zeros from that, because this is final. So we'd have to have some way to transition to this that accepts even numbers of zeros, but not odd numbers of zeros.
So this, because I can go 0, 0, 1, 0, 0.
Yeah, just for this, only characters that contain zeros, because as soon as we get a 1, we're not considering that anymore. So it's a more complicated language than just even numbers of zeros. But if there are no 1s in it, even numbers of zeros get accepted by themselves. So it's a good idea to start with, I think. And it's definitely ambitious. A 2-state solution. Is it possible this is really a 2-state DFA in hiding? My view on this is it's not quite as intuitively obvious. In fact, it's very intuitively difficult to see whether this can be reduced or not. So I use that as motivation to say, let's actually go through this process and see if we can remove any of these states. All right, let's go through it. So I'm probably going to switch back and forth, which makes me think that I probably just want to draw it somewhere. So I'm going to do that. I'm going to kind of draw this on the side. So we have a starting state, we have Q0, we have on a 0, we're moving to Q1. On a 1, we're moving to Q2. We have a 0 leading to a final state, Q3, back here on a 0. Same thing here, we move to this state only on a 0. Then we have Q4 out here, from Q1 on a 1, from Q3 on a 1, from Q2. Flip numbers, this is 2, this is 3. This on a 1, and this final loops to itself on a 0 or a 1. All right, let's actually go through the process then. So first thing to figure out, are there any inaccessible states? No, we can figure that out pretty quickly. We want to split the states into equivalence classes based on finality. So I'm going to kind of create a little table here of, it's going to start out as final and non-final. So this is kind of going to be group 1 and group 2. We may need some extra groups as we figure out whether they're distinguishable or not. But we know that non-final is Q0, Q1, and Q3, and final is Q2 and Q4. We already know there's no way these states can be the same. How do we know that Q2 is distinguishable from Q0? Well, on the string lambda, you end up in different finality. So there's no way that these two states can be the same. They already, one accepts, one rejects. Just the fact that you are there. So they're obviously different. So we have this equivalence class and we have this equivalence class. We'll call them non-final and final. All right, so we're going to start on reading a 0 and look at the pair Q0, Q1. Note that you only want to look at pairs within the same equivalence class. So we're going to start with Q0 and Q1 on reading a 0. What happens on a 0? So we're here and we're here. We're simultaneously going to read a 0 from both source nodes, states. So Q0 goes to Q1, Q1 goes to Q2. So we end up there. We're going to look at the equivalence classes of the destinations. Are they the same equivalence class or are they in a different equivalence class? Q1 and Q2. One of them is here, one of them is here. They're in different equivalence classes. So because we started with Q0 and Q1, we know that these are actually distinguishable. There's a reason to have both of these states independently of each other. So we're going to split one of them out into its own equivalence class. And again, I don't like how this is worded. Yes, they have different finality, that's easy to see. They are in different equivalence classes. That is the better way to state this. I'll edit this before it goes live so that it's a little bit clearer. So these states need to be in different equivalence classes. It doesn't matter which one of them you pull out, but we're going to make a new group 3. And heck, we're going to take Q0 and we're going to move Q0 into that group. To show that Q0 and Q1 are actually in different equivalent classes. You could also pull Q1 out. Doesn't matter. Let's look at the pair Q2, Q4. Now, actually, before I really pull this out, there's one more thing that I want to do. Let me make sure. We did this to really pull out Q0. You want to compare it to Q3 and say, are Q0 and Q3 equivalent? So if we do Q0 and Q3 on a 0, we end up there, which again are in different equivalence classes. So because this is distinguishable from this and distinguishable from this, we can move it into its own class. Really, what we'd be doing underneath the hood is coming up with pairs of states that are distinguishable and indistinguishable. So maybe this isn't really the best way to visualize this. Let me think about this for a second. So we really want to kind of make this a table. Maybe that's the better way to think of it. And I'm going to get myself into trouble by so we have a table here, and we want to mark those that are distinguishable and those that are indistinguishable. So the goal of this is to find all distinguishable pairs. So we know that, let's move back to here. We're going to mark everything distinguishable that is distinguishable. So we know Q0 and Q2 are distinguishable. And really, we don't need this whole thing. We really only need and we don't care about things with itself. We know that Q0 is indistinguishable from Q0. So we don't care about that, that, or that. So we really only need to answer everything else. Q0 and Q2 are distinguishable. Q0 and Q4 are distinguishable. Q1 and Q4 are distinguishable. And Q3 and Q4 are distinguishable. We want, should have done it this way, not that way. I have it done. Don't care about 1, 2. What do we have? 1 to 2. So this is gone, this is gone, this is gone, this is gone, this is gone. All right. Answering everything else here about all of those pairs. So we know distinguishable, distinguishable, distinguishable. We determined Q1, Q0 and Q1 were distinguishable. we determined that Q0 and Q3 were distinguishable. How about Q1 and Q2? On a 0, what happens from Q1 and Q2? They flip, but they're in different equivalence classes. So we found a string for which they are distinguishable. How about,
It's like that one's a final state and one's not, doesn't have anything to do with that.
it does initially, this is how we broke it down initially. But once we do this, we're gonna look at every row of this table, and if everything says distinguishable, then we're gonna move it into its own equivalence class. And then we're gonna loop through this again, only with pairs of states that we have question marks on. So Q1 and Q3, what happens on a 0? They merge into Q2, which is in the same, Q2 is in the same equivalence class as Q2. So we can't make any statement about the distinguishability of this right now. Have we proven that they're indistinguishable? No. But they're not distinguishable on a 0. What about Q1 and Q3 on a 1? So we read a 1, where do we end up? Both in Q4. Q4 is in the same equivalence class as Q4. So we actually can't say anything right now about Q1 and Q3. We need another iteration of this to be able to say anything about it. Let's look at Q2 and Q3. Well, they're already in different equivalent classes, so we know they're distinguishable. So we made all of these, so we now know that Q0 is different from everything, so it belongs in its own equivalence class. It's not actually here. Q1, we don't know if it's in the same equivalence class as Q3. Q2, we know is separate from Q4. Actually, we didn't ask that question, did we? For 2 and 4, what happens on a 0? Different equivalence classes between 1 and 4. Different finality, so we know they're distinguishable. How about 3 and 4? Well, they're already different, so those are distinguishable. So we've shown every pair here is distinguishable except for Q1 and Q3. So we're going to loop back around to the top, and we're going to say, all right, now is Q1 and Q3 distinguishable for everything? Based on the fact that we broke Q0 out into its own equivalence class, do we make any changes with that knowledge when we look at Q1 and Q3? And the answer is we still don't. So how do we show this? Q2, it was not Q2, it was Q1 and Q3. So on a 0, we end up here, same equivalence class. On a 1, we end up here, same equivalence class. Since this is the only question mark, we finished that having made no changes to these equivalence classes. That is what proves that these states are indistinguishable. This is a very important finding. It tells us that Q1 and Q3 can be reduced into a single state. How would we do that? What changes would we need to make to this to eliminate either Q1 or Q3?
Let's do a 1 from Q0 to. Add a 1 on the line that's going from 0 to 1.
Yeah, so if we're gonna eliminate Q3, every edge into Q3 also needs to be an edge into Q1. So we're going to add the edge here. Every edge out of Q1 needs to point at the same place that it pointed for Q3. That should involve no changes. So the fact that this 0 went here, great, it will continue to go there. The 1 that went here goes here, and now the the state itself, Q3, and every edge in or out of it can be removed. So we can say, this is gone, this is gone, this is gone, and that's gone. That is an equivalent DFA to what we started with. And this is the programmatic way to prove which states can be combined. If they are indistinguishable, then they can be combined. But you can't make that decision about indistinguishability until this whole process terminates. So we go distinguishable if we find such a way that they're distinguishable. We leave a question mark for anything we can't prove right now, whether it's distinguishable or indistinguishable. And once we go through this entire process of looking at every question mark that remains in this table and make no changes to our equivalence classes, we add no new distinguishabilities. Then we terminate and every question mark becomes an indistinguishable. I kind of jumped ahead of the slides, but that's basically what you do. I would say construct the table. You only need to look at every pair, not worrying about reversing that pair, because order doesn't matter here. So you're really only building kind of half a table. Doesn't matter which half of it is. Start everything out as a question mark. If you show that reading some character leads to two states that are in different equivalence classes, mark them as distinguishable. Once you go through that for every question mark, start over. Because every row that is distinguishable now, you can put them in different equivalence classes based on the result of this table. So we knew that we could split out Q0. And in fact, we can split out Q1 from this as well, because it's distinguishable from both of these. So it doesn't go here, it's distinguishable from this. So we had another class here, Q1. No, we didn't. They ended up the same. This is what happened. We ended up putting Q4 out here. So kind of we ended up with these equivalence classes in the end. Don't mind my second grade chicken scratch on the board. Actually, should mind it. I should do better, but I tend to have bad handwriting. I apologize. If there's anything I can clarify, let me know. Questions about the process? I kind of did it without slides, and now the slides just go back through all of this information. How do we feel about it now with the example? Sense of thumbs? So does the process make sense?
So is that the most reduced that DFA can be?
Yes.
Okay.
Everything else is distinguishable, which means there's a reason that it exists. So there may be some completely different DFA that is better, but starting where we were, this will reduce it to the simplest DFA that is equivalent to that one. And it's the simplest DFA that accepts this language. Yeah, it's cool. It's a cool process, but it's a little bit involved. If this were a semester and not a quarter, I would probably say code this up. But we'll have probably time for one big project in the class, and there's a more interesting algorithm than this that I want you to code up. All right. Last minute questions or clarifications? I'll just kind of quickly go through the last couple of slides here. How do you construct the equivalent, the minimal DFA, generate the equivalence classes for each set of indistinguishable states? We are going to concatenate the old state names, so you could actually write Q1, Q3, because it's basically, we combine them into one. all associated transitions in and out of any newly merged states. So the transitions that were in and out, we're gonna combine them. Sometimes you will find that the initial state is part of this. So if it is, the new initial state is defined to be the state that includes the original initial state in its concatenated name, which is why we kind of concatenate these. So if we combine like Q0 and Q2 at some point into a state, the start state, even if we got rid of Q0, would be the one that contained Q0. So here's where we would want to start. So we end up with a solution that looks like this. And that should be what we have here, just slightly different. This look equivalent.
There's no way you could like repeat the process to potentially find something smaller or anything like that?
That would have been counted in this,
Perfect.
yeah. You may do multiple of this when you find if there are multiple eyes in this chart, that means you're gonna be doing multiple, getting rid of multiple states, combining multiple states.
Makes sense.
Yeah, it's the same chart, just configured randomly.
Yeah. Yeah, I just kind of drew it. All right. We're out of time. I think this gets you everything that is on the first homework. I think we covered that through last time. I will be getting you a study guide because we have an exam a week from today. So I'll be getting you a study guide here shortly. One consideration with that is that we covered, because this quarter started on a Wednesday instead of a Monday, we've covered a little bit less than has historically been on the study guide for this. So I think I will just kind of reduce the scope of exam one and we'll see where that leads us. But that should be okay, I think. So look for a study guide. It'll just have the topics that we've covered. Create it kind of like a worksheet. You can go figure out what do all of these things, what are all of these, what do they do? And remember, you get a sheet of notes, so you can start making a sheet of notes at any point. Put whatever you find to be useful on that sheet of notes, because the exam will not be definitional. It will not be regurgitation based. It will be problems like this. Well, not this, because you haven't had a homework on it, but problems like the homework, where unless you have written down the exact problem there, it's not going to help you. So the sheet should be helping you to make sense out of how do we do each of these things in general so that you can apply it on the exam. Because obviously the internet has algorithms on it. You shouldn't need to memorize them. It has definitions. You shouldn't need to memorize those. It's just a matter of can you apply what you've learned to produce a correct response on a problem you haven't seen before. So, all right. Have a good weekend. I'll see you on Monday.
Thank you, Professor.
Thank you.